predict with the bigger size.
Mm.
So there we got actually 8 by 8 into 4.
Mm.
What exactly that contains? There was a little bit misunderstanding.
Okay. So so why we are actually training on a small image, and then why are we actually trying to do it on a big image? That's the question, right?
Not exactly, but there is a possibility, right? We will train on a smaller image, and there is a possibility that we need to predict with the bigger image.
The problem there is, right, actually to identify an object or classify an object, we need to have closely cropped images. Suppose that you want to identify number plate in a car, right? First, you
Yes.
need to take only number plate images, and then train a model, right? And
Yeah.
then use that number plate recognition model to identify number plate on a car image. So car will be big image, right? And
Yeah.
then on that big image, you need to do sliding window, and where exactly that number plate you find, there you need to take it out, or you need to identify the object and then cut it. Okay, that's the concept, actual concept, right? In real
Yeah.
time. So number plate image is going to be small, right? Like this. If you build a fully convolutional neural network, then you can use these weights to identify the number plate on the bigger image. This is called as you look only once. YOLO algorithm. Basics of YOLO algorithm. You look only once, right? So that is like, this is a picture which you are trying to find on a bigger image, and you just look at it, look at that area, look at that area. One area you are looking at only once. That's the YOLO algorithm. Okay. And here the outcome is a 1 by 1 by 4 or 4 by 1 by 1, right? In NumPy matrix dimensionality, 4 by 1 by 1. 1 by 1 is the matrix, and then 4 is the depth, right?
Yeah.
So if you take a bigger image and try to train, these kinds of 4 by 1 by 1s will be more, because there will be many areas of, this kind of small picture, there will be many areas, right? So each area you are trying to predict one of the class is present or not. Each area you are choosing and trying to predict whether the class is present or not. So in this 28 by 28 by 3, we got 4 by 8 by 8 NumPy array dimensionality, 4 by 8 by 8 or 8 by 8 by 4. 4 is the depth. So each 8 by 8 cell, right? 8 by 8 means 64 cells. Each cell, whether the particular object is present or not, we are actually predicting.
So here we thought, like, there are this example we discussed about the prediction of the animals.
Ah.
So in the single image, we thought there were 4 images, 4 objects,
Hmm.
and we are trying to predict whether all of them are there or not.
Ah. One of them is present
So
or not. Yeah. In a given cell, one of
yeah,
them is present or not.
yeah, so here
Yeah.
it is 8 by 8 matrix, right?
Ah.
So this 8 by 8 matrix could contain one of the objects.
Oh, it will say, if in the first one 8 by 8 matrix, if you have one here,
Mm-hmm.
rest all are going to be zero only. Second 8 by 8, third 8 by 8, and fourth 8 by 8 is going to be zero only, because in that area we have only one object.
Okay, so if in the first 8 by 8 matrix, the first cell,
Hmm.
1 by 1, first row and first column is 1,
Hmm.
then the first row and first column of the 3 other matrix, 8 by 8
Ah.
matrices will be 0.
Yellow, pink and violet, right?
Yeah.
If blue one has got one,
Mhm.
yellow, pink, and violet will have zero, because the class we have chosen is the target variable class. The class is softmax. Right? It's a multi class classification. If you are saying, right, there may be one here, and in the orange, the what do you call it as the pink color also, if you have one, can we have that kind of situation? Yes, we can. If you take the target variable multi-output classification, right? Target variable, target the activation function or the network structure you choose in such a way that it does the multi output activity. Multi output, if you have to do, what you need to do, each of these cells will be a binary class,
Yeah,
or
zero or
each
one.
each of the cell is going to be a softmax regression classifier. Got it?
Yeah.
If you have multiple classes, I actually said 4 animals, right? 4 animals means 4 classes. Each cell can have either 0 or 1 or 2 or 3 or 4, right? Or yeah, this is another way. Sorry, no, I'm confused. I'm confused and I'm making confused. So here, right, you can actually take the target variable for what you call it as the sigmoid function. This one sigmoid, this one sigmoid. Then you can have one here, 0 here, 0 here, or 1 1 0 0 like that, right? So in a all 4 objects can have one, because in a single place, in a single cell, there may be a possibility that four animals are present, right? Maybe elephant and horse, in front of it a cat, and in front of it a dog and a cat, right? These are all bigger image, small image, like that. There can be one in one cell. There can be 4 images also. In that case, you will get all 4 ones. You can do that also. It depends on the way we design the network. If you take each cell, each output node is a sigmoid node, you can do that multi-label classification. Here I chose softmax regression classifier, so it is a multi-class only. So one of them will have 1, rest all are going to be 0. Got it?
Yeah, sir. So what this 8 by 8 by 4, how the predictions will happen? So are we sending this to anything else, or?
Again, threshold only, right? It's a softmax regression classifier will give you probabilities.
Mhm.
Use threshold and make prediction. That's what I showed you in this no number, what you call it as
Coding.
OCR, right? OCR model, fully connected this thing. Now I have built a network on small image,
Yeah.
and I have taken this bigger picture. This one, right? This is a big picture where you have, this. You can think 5 as a dog, 2 as a cat, 7 as a elephant, and like that, right? So there are different different objects in the image, and we are sliding through and then trying to find, because we did not use non-max suppression, right? Intersection or union, those concepts. We are getting multiple times these numbers. 85 by 85 number of times it is actually doing the sliding, and we are getting multiple times these numbers, because if we apply that non-max suppression and intersection or union also, we would have got less number of numbers. Got it? Non-max suppression means um, intersection or union. Let me try to show that picture and talk. Where is that? Yeah, this is the intersection over union. So suppose that this dark place 5 is there, and the model is finding 5 here, right? And it will slide, right? Somewhere here also it will find, somewhere here also it will find, somewhere here also it will find. Out of all those, right, which one gives you the maximum intersection over union? You consider that, right?
Yeah.
to consider, consider whether that bounding box is correct or not, you do non-max suppression. There may be many places where 5 would have found or dog would have found, but all those boundaries you will not consider. Only those boundaries which are greater than 0.5 or 0.6 you will consider. Out of those you take the maximum one and then do a bounding box. Got it?
Yes, sir. So the 8 by 8 matrix, what exactly it contains, sir? It contains only zeros and ones?
These
Or, okay.
8 by 8 matrix will have elephant, dog, elephant, elephant, dog, dog, like that.
Okay. So one single 8 by 8 matrix can contain
One 8 by 8 matrix is can contain, maybe in consecutive 3 cells, elephant only.
okay.
But you need to decide, you need to take the best one out of these 3, or maybe, out of on all these 6 it may find elephant. Okay, one in all these 6 in an elephant, right? So you need to decide which cell to finalize. Okay, which cell to finalize is like using non-max suppression and intersection or union. You decide. Got it?
Okay. So this 8 by 8 out of 64 elements, we will take only one.
Ah,
We will get only the one class.
one class only. Wherever you find one in this, right, there you find one class. So here in our example, right, there are no channels there, and I did not even took channels there. The network is in a different way, right? If you look at this network, so output layer, yeah, softmax 10. Give me one sec. Ten classes, right? So yeah, I actually applied this. I am getting the same thing here, right? Like this. Here I get 4 depth, right? I have got 10 depth there. But I took argmax of the axis 2. 0 is rows, 1 is columns, and 2 is the depth. Let me try to show you. See this? 85 by 85 by 10 I got, right? So in this, see this argmax axis is equal to 3. Sorry, there are 4 dimensions, right? So 1 by, so 4th dimension is this one. So in the depth I have taken the argmax. That means, if you look at this picture, there will be probability here, there will be probability here, there will be probability here, and there will be probability here. Whichever probability is high, the record belongs to that particular class. Right? There are 10 of them in our example, in our handwritten digit recognition example. Right? I took argmax in this direction. So if you want to yeah, go ahead.
Yes.
Go ahead, Andy.
So here actually, okay, sir, you complete.
No, I was actually about to say that, if you want to engulf everything and understand clearly, look at YOLO 3 documentation and then try to match this one with that. I am actually trying to demystify YOLO 3 algorithm a little bit.
Okay.
No need to understand it completely, but this is the basis. If you understand this concept, right, You can do OCR model. We actually did number plate recognition model on our own. We understood it, so we were able to do it. Right? This is number plate recognition only, right? This is suppose that this is a big car and there is a sheet with number plates. These are all number plates, right? We trained model on number plate first, and then we are actually sliding it through this, and we used pre-built models. So how is it happening? If you know, when you are using algorithm, it becomes easy. No need to understand completely. I did not implement non-max suppression and intersection or union and grids and all that. I just did that sliding thing. That's it. Got it?
Yes, sir.
Yeah, it's good that you are trying to understand it, right? It's good. Yeah, please.
Yeah. So here the input actually has 16 numbers, right?
16 images, yeah. 16 numbers,
Yeah,
yeah.
16 objects
Yeah.
in the picture.
Uh,
But we got the output as 85 by 85 by 10.
Out of these 85 by 85, 4 by 4 is the correct one. So using intersection or union and non-max suppression, you need to find out those 4 by 4. That's the key difference between the pre-built algorithms and us.
Yeah.
Right? So if I have to do that, I have to spend like around maybe 4 or 5 days in coding and intense thinking and all that. I I I did till some extent, and I did not do it. But these guys, right, whoever that YOLO, RCN and fast RCN, and these are all algorithms. They implemented all that concept you're actually thinking of.
Yeah. So, but the
Yeah.
output of this image will be at the end. It should be a 16 numbers, right, sir?
Yes, sir. If you use pre-built algorithm like YOLO 5 or YOLO 4 or 3, it will give 4 by 4 only. 4 by 4 outcome only.
Okay, 4 by 4 means 16. Okay, in each place it tells what is the digit.
Yes. Whatever the predicted digit, it will show.
Okay.
It may be right, it may be wrong.
Yeah. So again, how to identify the accuracy, sir? If
Accuracy.
yeah.
Yeah, we know which object we identified here, right? And this is a cost function will be there, right? Between all the input, what pictures you pass, what objects are present. Output also knew what objects the model has predicted. Right? Then you write a cost function around it. That's a complex thing, actually. What you're asking is, implementation will take time. If we have
Yeah.
to implement everything on our own, it will take time. But it is not impossible. Right? If we spend a month or so, it's a research topic basically, right? If we are not working or not working on a project right now, we'll have time. We'll have time and we can do research and produce a new algorithm to do object detection. There are many algorithms for object detection. Model Zoo, TensorFlow Model Zoo is there. So these are all the object detection models, and the number of frames per second it processes, and all that. So you can actually download these and use them directly. So how they happen, how they do, this is how they do. They already have trained a model on multiple objects, and then they are doing this sliding window thing on the bigger image. And what is the advantage of using the pre-existing model? The weights are already trained, and they know what is an object and what is not an object. If you train with your data, even if the data is less, the model will work good. We actually have a lot of work around this, and we are trying for a bigger one. Right? If we get that right, we'll have huge amount of work around this object detection. And we have plans to do robotics also, self-adjusting robots, and in controlled environment, to perform activity. Right? There will be, there will be coming all these things. So we actually are thinking of it, one step at a time. So we'll have a lot of work in this. So why am I trying to tell this is, this object detection is the basis for robots to identify and move. So there are two steps in for a robo hand to move. One is how far the robo is from the place it need to go. That is one thing it need to identify. And then when it is actually moving, whether the target is also moving or not. That's another thing. It need to track the target, right? And when it reaches the place, right, hand should know where exactly it should move to. So the direction and the length also it should know. So these all things come under object detection and some math around it. Some math like Kalman filter. There are some filters there, and there is calibration. We call it as if you take a picture will have pixels, and in real world, right, it's a 3D world. You will have length, height, and width, right? 3 dimensions you will have. But in a 2-dimensional picture of the same 3-dimensional object, you will have pixels xy only. Right? You need to understand the relation between. When you take a picture, there is a measurement, real measurement, that actually was taken as a picture, right? So you need to understand the the correlation between the pictures. In a direction, if camera is there and you are taking multiple pictures, real dimensions and the pixels will have some relationship, right? Do you agree? You fixed your camera, okay, and
Yeah.
then the pictures were taken. 100 pictures were taken in a day, right? And now the dimensions of the real world and the 100 pictures will have correlation. Do you agree?
Yes, yes. It
Right?
should.
That correlation, finding out the correlation is called as calibration, camera calibration. You do camera calibration and understand, how things are there in real world, and accordingly you perform the activity. Speed detection, this is the basis. So we fix the camera. If camera is also moving, that means robo is also moving, right? Then it's a bit difficult thing. We need to take the sensors, IoT, right? IoT sensors help to do more, right? It's a more complex thing, than speed detection. So if your camera is fixed, you know the physical dimensionality of the road, right? And then vehicles are moving, right? You need to track vehicles, identify a object. Person is moving, no, you will not care. Bicycle is moving, you don't care. A bike is moving, a car is moving, you need to identify the object, detect the object, then track the object, and you need to have that correlation between the picture and the object, and then you can identify how far the vehicle moved in how much time. That's the speed. Got it? This is the basis
Yeah.
for whole thing.
Yes.
Yeah, there is some problem we are facing right now. Number plate recognition was not happening right. So there is a lot of research that need, research help we need. So Seshram Gar, if you have time, right, try to work with the uh, model zoo, one of the models from model zoo, right? Maybe mobile net or whatever, right? So I gave you that TensorFlow object detection API tutorial, right? This one, you follow this one and do one model, you will get a lot of confidence. Okay. You can do this on collab also.
Yes, sir.
Narayan garu. Hello.
Sir.
Sir, manaku pani undi ippudu. I mean, we have work to do. So, if you follow this TensorFlow 2 object detection, whatever, and do one model, then we have work to do. Number plate recognition was not happening right. So we need some research in that area, right? So that is one critical thing actually we are trying to address now. If you two can help me, right, that will be a lot of help.
Yeah, sure, sir. We'll do that.
So definitely do this, Andy. Definitely do this. And I have today I'll explain one more concept as face recognition. I don't know whether the other people are actually following the videos or not. This is by mistake actually. My mistake that I am unable to take classes on the weekdays and taking class in the weekend. These are all very. This is the core. For this only we spent almost 4.5 months to do these things only. We spent a lot of time in learning all the fundamentals. Now the time came to do the real stuff. People are not joining the class. That's bad. I don't know. Yeah. Any other questions, Sunday? Are we good?
One more clarification, sir.
Please,
So
yeah.
we are actually applying stride and pulling to reduce the dimensions, right?
Avunandi, yeah.
So does pulling has the weights? I don't think pulling
No,
has the weights.
pooling has no weight. That's where we
No weights.
consider this.
Average or max.
No, yeah, average or maximum. Max pooling is the one many times used. That's where you consider these two as one layer.
Yeah. So what is the difference, or what is the benefit, or when to use what? So the
It depends, it's like your image is too big and there is too much noise and you don't care about that. Then you apply stride, bigger stride and max pooling to
okay,
reduce the dimensionality quickly.
both for the same purpose, or any specific cases we need to use stride, or some other specific cases we need to use pooling.
It is all trial and error, Andy. Yeah, there is
Okay.
no specific this thing. This is like the neural network is a black box. We are actually trying to open it and see as much as we can, and we are thinking along, right? So in mind, we are actually thinking a lot. Instead of whatever I showed is nothing, but the way we think and understand is more, right? So we cannot think too much. So what we do is we do the hyperparameter tuning, right? We put different kinds of networks and train the model and all that.
Yes, sir. I'm done, sir.
Yeah. So this is like this class, right? This object detection thing, right? This OCR thing is kind of research work actually, right? If you want to do, you can spend more time. I actually spent good enough time on this. Maybe around 3 days I spent and tried to build this. And today I'm going to show you face recognition model. That also I worked on. I worked on all the models with the numbers only, the handwritten digits only, because you already know the data set. Instead of handwritten digits, you need to use other, right? Other maybe number plate numbers or the see film heroes numbers, photos. So it's an exercise, right? So when you do that, right, you will get confidence and you will get full control. So that's where I kind of took the simple example and did it. Okay, the effort is same, right? The network structure may change, and you may have to trial and error multiple times, right? But the effort is same. Whether you do it on handwritten digit or a film actor, effort is same. So let us move on and try to understand what is face recognition and what is face verification. Okay, this is one of the requirements from our client. We actually did a base model using pre-trained whatever junk, but I am not satisfied there. I wanted to do our own model and then maybe kind of do more stuff on that. But we did the basic one, and we had to demonstrate. We will demonstrate it, but that's not an urgent thing. Now we are trying to solve that number plate stuff. So once the cars thing is done, right, we'll jump into that. But I have a basic implementation of the face recognition. I'll show you. Okay, Siamese network we call it as. So face verification means you pass a person image and ID, it will tell whether the person is present in the database or not. Both are same. They name it differently and they ask in interviews. So I kept it here. So face verification means you pass image and ID both. It will say whether whether it is present in the database or not. Face recognition means you pass image only, and then it will check against k images in the database and output name or ID. Okay, whether it is there or not. If it is there, you will ID, return ID. If it is not there, you return null. Doesn't matter, right? So face recognition and face verification, they named it differently to confuse people. Both are kind of similar. Okay. So we have seen VGG16, right? Can we do face recognition models with VGG16 cat dog classification? Cat dog classification model we did, right? Can we do?
I think yes.
Yes, right? How
Yes,
do you
sir.
do that?
So you can create the boundaries at the face level instead of the entire picture.
I'm talking about VGG16, the cat dog classification we did before we actually started this object detection, right?
Yes,
We
yes.
did cat dog classification, VGG16 model. Let me show you. I think this one. This one, right? I trained, VG16 model. I have taken transfer learning. We did transfer learning and then, trained the model and tried to predict whether cat is present or dog is present in the image or not. This is a closely cropped image. So in face recognition also, suppose that you have taken closely cropped images of employees of an organization, right? And then you wanted to do the face recognition model. Can we use VGG16? If yes, how should we prepare the data and what are the requirements? Right? How should we prepare the data and how should we start training? So suppose that we four are there. We four are there in an organization. We want to build. When a picture is passed, it need to predict whether it is Rama or Sishiram or Narayana or Girigar, right? So to do that, what you need to do, cat dog classification, what we have collected?
The cropped images.
Cropped images of cat and dog, right? Like that, we need to collect cropped images of all four of us, right?
Yes, sir.
Maybe, maybe 15 each. And then, you pass that, you create a data set, you convert that data into what I did here. I converted cat image, dog image into pixels, right? Like this dimensionality, 224 by 224 by 3. My image, I'll convert, Girgar image also and, Seshiram Gar and Narayana. Everybody's images I'll convert into 224 by 224 by 3. Suppose that for each person I have collected 20 images, right? Each image I label it, right? Because I know that it's me or Girgar or somebody, right? I'll label it. Right? That's how I prepare data. Now I pass those images into the same network. Got it? Same network. The target variable here, the last layer is softmax only. So, you pass n number of classes and data, right? So, dense layer 2. So we have to take, 4 here, right? 4 classes, so 4 here we have to take. We train the model. Now you pass a picture of one of us 4, it will predict, right? That is face recognition, right? Face recognition done, right? But is there any problem with this? Now, right now maybe Prithvi joined our company. Now I need to predict whether Prithvi, I need to pass Prithvi's picture and need to make the model identify. What I should do? See, first problem is solved. You understood, right? First problem, we four are there in the organization. Give me 1 second. Sorry for that. And you understood the first solution, right? You understood, right? How to use VGG16 to do face detection, face recognition. Understood?
Yes, sir.
Yes,
Right?
sir.
Give me 1 second. Hello? Hello? Yeah. No need, Amma. పొద్దున్నే మొదలు పెట్టేశారు వీళ్ళు 9:30కి. Okay. So now a new person joined in the organization. What we should do? To make the model identify the new person, what we should do? A new person joined now.
When you take the cropped image of that person, maybe one or more,
Ah.
add it to the training.
Need to do retraining again, right?
Yes.
Yes.
Right?
Yeah.
Only with that person, or do we need to add our photos also, our four also?
Or four not required.
No, sir. It's
Any
required, right? It's a,
Okay.
It is required. If you don't pass our four, right, the model will identify that person only. It will forget us.
Agree, sir. Yeah, we need to, yeah.
So
it
if
will
you have
overfit.
not overfit, the model weights will change completely,
Yeah,
and
yeah.
then it will identify that new person only, not us. So
Yes.
if you have 1,000 people in your company and for each person you have taken 20 pictures, 20,000 images, and one person joined, right? You need to train the whole model on all those 20,000 plus 20,020 images. So it will again run for 5 hours. Right? Tomorrow one more person joined. Maybe morning one person, evening one person joined. Right? Every time you start training. So that's the problem with VGG16. Okay. In some of the videos on YouTube, right? These guys are showing this as the object detection model, face recognition model. It's not going to work in real time. Okay. So that's the problem with VGG16 kind of networks trying to do face recognition. Okay. So the solution. Right? We'll see the solution now. The solution is one-shot learning. The name is given as one-shot learning. Okay, face recognition. In this, what we do is my picture, maybe 4 pictures of mine I'll take, and try to generate a 128 dimensional vector out of my picture. Right? My picture is 224 by 224 by 3. Think that maybe 500 by 500 by 3. 500 by 500 by 3 means 75,000 pixels, my picture, right? 75,000 pixels. I am actually reducing the dimensionality to 128 pictures. The way I reduce the dimensionality is by taking my pictures, 4 my pictures, or maybe 1, maybe 2 pictures of mine, right? And there will be other people, right? If you take our example only, we 4 are there, right? For me, I take 2 pictures. For Girigaru 2, Sheshigaru 2, and Narayana 2, right? Narayana 2. So I have 8 pictures now. So I take my picture and my picture itself and try to run some network and reduce the dimensionality. Okay? And pass my picture and Girigaru picture, run network, again come to the same dimensionality. Like that, right? I take my picture, one positive. My picture and my picture is called as positive example. My picture and Girigaru picture is called as negative example. I take a positive example and negative example and run this network and reduce the dimensionality. I'll talk about this in more detail. At a high level, I am talking right now. I have code also for this. Okay. So this is called the embedding. The vector representation, the reduced dimensionality vector representation is called as embedding. We do embeddings on the text also, right? The next topic is going to be word embeddings only. This is image embedding. Okay. So every person comes in. I have 1,000 people in my company. I take 2 images for each person and try to create a data set like for each person two samples, one positive sample, one negative sample. What is positive sample? My picture and my picture target 1. My picture and Girigaru picture target 0. Seshiram picture, my picture target 0. Seshiram and Seshiram target 1. Like that, right? We 4 are there, so we'll get 8 records. If 1,000 people are there, 2,000 records we'll get. And then we train a network called as one-shot learning network, and we'll reduce the dimensionality to 128 pixels. Okay. So now for 4 of us, we'll have 4 vectors in the database. 4 128 picture, 128 pixel reduced dimension, not pixels, reduced dimensionality vector representation in our database. Now I came and stood in front of the camera. The camera will take my picture and pass it to this network and generate this 128 vector and check against the database. Euclidean distance between this new 128 dimensional vector and the 4 vectors. If it finds the closest vector, right, it says the person is belongs to organization. If not, it is not going to do it. Okay. So what is the advantage here? Now new person came in. When new person comes in, right, we will not train the whole network. We'll train on that person's positive and negative image only, and generate this 128 pixel whatever. Or even we don't even train it. We'll have a network where we'll pass the images, and it will actually generate 128 pixel, 128 vector representation. Right? If the model is not working properly, right, you take all the data. Maybe 1,000 people you did the model, your company became 1,500. Right now the model is kind of working haywire. you need to regenerate whole data and retrain the 128 pixel generating network. This is a separate network which actually generates 128 pixels of each person, and then it saves into the database. There will be another network which actually takes the, this is the network actually. There is another network there is another calculation which actually takes this 128 pixels and compares it against the database. So if you have 1000 people in your database, you take current person, whoever is in front of cameras, 128 pixels, do 1000 calculations, 1000 Euclidean distance calculation. Whichever is, we take the closest one and then decide whether the person belongs to organization or not. Did you get it? Did you get it? The gist of it, did you get it? At a high level?
Yes, sir.
Right? Instead of training the whole network with all the people, we are actually using a simple network to generate an embedding, image embedding, and using that image embedding, we are actually trying to check against the database. Okay, so in the database, you put this 128 pixels, that person is going to be there in the organization. If the 128 pixels are not present in your database, that person is not in the organization. Okay, let us look at the theory and then I'll show you the code example also. On handwritten digits only I have done it. I'll show that example. We have to do this. Actually, there are databases for this face detection. We can actually, we can use my code and then do it for the network. Network size will increase. That's it. Okay. So build a CNN network to identify each person is not a good solution. If new person comes into the, comes into the organization, need to train the whole model again, right? That's the problem we have seen with the VG16's transfer learning, right? So the solution is Siamese network, which actually generates a 128 pixel representation of the picture. Okay, so let us look at the Siamese network code and then come back to it. Come back to theory.
Sir, one second, sir.
Yeah, go ahead.
Sir, is it 125 a standard? I don't think, right?
No, it is not standard.
Yeah, so I was thinking if we represent an image with the 128 vector, and if the number of people are increasing, it may result, multiple persons, or the Euclidean distance against the two records of a database may be same.
We'll come to that. We'll try to make the network a little stringent by adding a parameter called as alpha. There is a hyperparameter that actually makes sure that these 128 representation, vector representation, will not fall close to each other. Okay, I will see that. We'll see that. Your question is very valid, and we'll see that in a moment.
Okay.
So let me show you this Siamese network. Okay. Give me 1 second. So I forget. I actually do it and leave it, right? So I forget. Give me 1 second. Okay, so I have taken taken this data set. So I said that there is a positive image, there's a positive sample and negative sample, right? That concept I'll explain first. So I said, I think we need to, yeah. So there is a concept called as triplet loss. Okay, how it works is you take an image A, we call it as anchor tag. You take an image P, positive image, right? My image, anchor tag. My image itself, another image, my picture, other picture has positive image, and maybe Sesiram's image has the negative image, right? And then we create two records. Okay, one record with this like this, my image and my image itself, and my image and Sesiram's image, and I pass it right? And then try to do a sigmoid function to actually generate these 128 pixels, right? We actually have to build this network. Okay, so let me show you that. I'm actually, so a row with anchor, positive, anchor and negative, two rows. Okay, label anchor and positive as 1, anchor and negative as 0, encode image using Siamese network, and then there is a cast function, right? There is a cast function which is triplet class. This is the cast function. So we'll come to that. This is actually back and forth stuff. So I'm kind of going back and forth, right? So this last function will make sure that these 128 representations are actually generated properly. Okay. So when I am doing it for this person, this 128 is the thing I am actually going to save into database. Okay. So let me try to show you the code. It will give you more clarity. It will give us more clarity. So I loaded the data and then I did normalization, right? This is a normalization. Do you agree? I took the maximum number and then dividing each of the cells with that maximum number, right? So the shape of the image is 28 by 28, handwritten digit only. Okay. So I am actually trying to see where all the 5 is present. Okay. In NumPy, there is a method called, there is a function called as where, which actually gives you the indexes. Okay, indexes of all the images that are. Try to run this and show you. So it gives you all the indexes of the see that where is going to give you a tuple where there is an array of indexes and so there is nothing there. So I actually accessed 0 because I wanted to see the array of indexes where 5 is present. Okay, so I have taken one example 5, right? The y value 5, right? In that index, the x belongs to 5 and y is actually 5. Okay, and then random choice is a function which actually randomly chooses one number. So if I run it multiple times, it actually takes a different number from the given set. I'm going to use this, I think. Maybe that's where. So randint, I don't know, right? So here make pairs. I'm actually trying to create these positive and negative samples. Okay. So how do I do that? I have written some code here, right? Make pairs. So I have taken, yeah. So for each class, right, NP where y is equal to I. That means for each class, I am trying to take, right, this range of classes is the 0 to 9. So I am taking, for 0 class, all the indexes I have taken, digit indexes, right? And then for one class, I have taken all digit indexes. For two class, so there is a two-dimensional array with the first row belonging to all 0 classes, second row like that it is. Okay. Now I am actually forming the pairs. So from the I have chosen one image belonging to that particular class, right? I need to actually form this positive record and negative record, right? So positive record means I need to take the image. Sorry. Suppose that I have taken a record belonging to 5. I have to take 5 only, right? Another record belonging to 5 only. See this here? I have taken a 5 image and then I have randomly chosen another 5 image and combined those two. I'm putting it in the pairs and label I gave as 1. Okay, and I am taking add no match example. I have taken this x already which is belonging to 5. So I have taken class -1, right, that other example, and then I am pairing it and putting 0. The gist is that I am taking the x values of 2 records belonging to 5 and putting the label as 1, two records belonging to 5 and not 5, giving 0. In this example, right? Taken this person and this person's picture and kept the final target variable as 1. Took this person and other person, kept the target variable as 0. Did you understood? Make pairs method is actually forming those pairs. Understood? Yes, no?
Yes, sir. Yes, sir.
So, what is the dimensionality of this data set? Let me see, somewhere I would have kept. So, make pairs. Right, there are 60,000 images in the training set. Okay. When we did pairs, right, we have got 1,20,000. I said, if we take 4 of our pictures and try to do this Siamese network, we'll get 8 records, right? These are the double records. Got it? So here there is a depth 2. 28 by 28, depth 2. First image is the anchor image. First layer is the anchor layer. Sorry, channel. First channel is anchor channel. Second channel is either positive or negative. Got it? The structure. Okay. Now the labels are same. So the make pairs work well, right? Make pairs of 0, 0, right, is 5. Make pairs of 0, 1 is 5. Right. Now make label train is equal label is equal to 1. So I have taken a negative example here. So some index, right? 1, 1, 1. So you see this negative, right? Negative sample. And now the target will be 0. Got it? From this array, the newly formed array, I am trying to show one record, one positive record, where both are 5s. Right? These are pixels. I am actually trying to show them as picture. And the target variable is 1. Okay. And one is 5, negative, negative image, anchor tag and negative image, anchor image and negative image, target variable 0. Now we need to build this network. What network? This network we need to build. Okay. So let me show you that network. So I have taken sequential class, flattened, right?
Sir, one second,
Input.
sir.
Yeah, please.
So, what exactly the anchor tag? Is it an empty image?
No, anchor image is the 5 here. Positive
Okay.
image is also 5, so we gave 1 as the label. Anchor image 5, positive image, negative image is 2, we gave 0. We formed this kind of data set from the original data.
Okay. So if the anchor image and the other image are both are same, then we are saying positive.
Yeah, see this? This is 1 anchor and the positive image, anchor and a negative image. For the same record, I actually did 2. I think this is a different one. So actually, we can actually find that also. I have to write a lot of code there, so I kind of took some random thing and tried to show. Got it? These 2 records belong to same one record. We actually made it into 2 records by adding positive and negative images.
Okay. Okay.
For our face detection also, you have to take my picture, put 1, my picture, Girigaru picture 0, right? Your picture 1, your picture maybe Narayana picture 0. Like that you need to form the data set.
Yeah.
Got it?
Yes, sir.
Now I have done 2 models. I don't know why. We'll see. Why I did that. I will see. So here I have taken a sequential class and then 2 sequential classes, right? And then concatenating them with model. Okay, 2 sequential classes. Now I am taking input and then dense layer. See this here? I am taking input and suddenly I added dense layer, right? I haven't added any convolutional neural network because the problem is not that complex, right? This image, the handwritten digit recognition is not that complex. So I did not add any of these layers. I took directly this 128 pixels, so 128 node layer, right? Input I am passing 128 layer, input I am passing 128 layer, right? So this is the network, okay? And then I am concatenating these two outputs, right? I am concatenating these two outputs, right? Like this. I am not like this, but I am concatenating. And then I passed the concatenated one to sigmoid layer. Okay, that's the network. I concatenated these two and passed it to sigmoid layer. Okay, so the model is going to, we have to take model only because sequential cannot work with these complex networks, right? So I have taken model class. I am taking inputs as a sequence input, right? Sequence 1's input and sequence 2's input, and output is the dense layer. This dense layer. So this is the sigmoid layer. If you visualize, if you want to visualize, suppose that these all things are not there. So let me take a screenshot and explain. So this is the core of it, and nobody takes pain in explaining this because many people don't even understand what's going on there. Okay, so suppose, right, these layers are not there, and this is 5, right? This is 5 or 2 or maybe any other class. Okay, this is all not there. This all thing is not there. Oh, this all thing is not there. Okay, so directly passing this and then merging it and passing it to sigmoid layer. So to do this network, I used sequential and model both. Okay, and I used binary cross entropy, because I would have converted the target variable into maybe this one hot. I don't know. I haven't seen it, but binary cross entropy is working. So I have this is actually the pre-existing cost function I'm using. In the next network, right, I'll use my own cost function. I'll show you in a moment. Okay, so I trained this model, right? I trained this model. This can actually generate the if you want to take the output, right, you need to take output from here, right? This sequence once this layer's output is going to represent your image, your pictures 128 pixels. Okay, so that is one example. Let me go to second example also. This is even more complex. Okay, not the cost function. I've actually taken a lambda layer, right? This is a new thing we are trying to understand. Lambda layers are very useful, and in cases where you wanted to very more complex networks. So I have taken a input layer, flattened it, passed it to dense, right? And I created a dense class, right? So I passed input and created dense class. What am I doing here? Give me 1 second. Okay. So this is actually, I should have written a class here. Okay, I should have written a class, but I did a simple thing here. If I create a class and then I can create instances of it. Two dense layers of same structure. See this here in the network. This network structure and this network structure are same, right? Do you agree? The networks parallelly moving, they both have same structure, right? Do you agree? Do you agree? Yes, no?
Yes, sir.
So you can create a class to generate this network, right? You can create a class to generate this network and instantiate, and then you can merge them two and do that. That kind of a thing I'm doing here. So I created some statements to kind of class creation, and then I'm I am creating two instances here. Input 1, input 2 I am passing. To the same network I am passing input 1. One network got created, input 2 I am passing, right? Two networks got created. Now, the merge layer, what I am doing is I am doing Euclidean distance. Okay, Euclidean distance and then sigmoid. Right, yeah. So here, this Euclidean distance method will take the vectors, dense 1's outcome and dense 2's outcome. These two outcomes it will take. Okay, these two outcomes it will take, and then it is trying to calculate Euclidean distance only, squared difference between these two vectors across axis 1, and then it is summing it. Okay, got it? This is Euclidean distance only, but square root we did not apply. Square sum, if you apply square root also, it becomes Euclidean distance only. Got it? What is formula for Euclidean distance? Square root of x1 minus p1 square plus x2 minus p2 square plus x3 minus p3 square and xn minus pn square, right? So here we are doing x minus y square and summing it, but not applied square root. Kind of Euclidean distance only. Right? You see here we applied square root, we applied, right? So we are applying square root to the sum of squares comma epsilon, maximum of each of these. So we are worried that we may get negative. So somebody, I don't know, will not get negative. Even if it is 0, not a problem, right? Why did I took this? I think it is not needed. Right? Guys, are you thinking? So I'm saying that function is not needed because negative number square root is not calculatable. Right? Square root of negative number can we calculate? Can we calculate square root of a negative number? That's a question.
I don't think, because a negative number into negative number, when we do the square, it is a positive number.
Yes, certainly. Can we calculate square root of a negative number? It is impossible to find square root of a negative number. Right? So here, right, I am actually taking maximum of the result comma epsilon. If it is negative, right, I will take that epsilon and try to calculate it. So we are actually squaring, right, the difference. So how will we get a negative number? No need to do this, right? So somebody would have written it and I would have copied it. So that's the problem. So no need to take this maximum and epsilon junk is not needed. And that is Euclidean distance formula. Okay, this is Euclidean distance I implemented. So I am taking Euclidean distance between, first I am passing the data through the network and then taking the 128 pixels and taking the Euclidean distance and then passing it to the target variable sigmoid, right? So this is actually, before doing this Euclidean distance I am taking, let me see. Yeah, to do this actually, okay, to do triplet loss, right, we actually have to do. So the first network is not actually doing the Euclidean distance stuff. It is a simple network that actually trying to generate 256 pixels out of right, when you pass two same images, it will try to generate one. When you pass two different images, it will try to generate 0. So weights actually understood whether the person is same or not. Okay, but here we are trying to make it more complex by adding this Euclidean distance function. Before we um, pass the pixels into the sigmoid function, we are calculating one number and passing it. Okay, this is one number. When you pass the 128 pixels to this Euclidean distance, you will get one number. I am passing that one number to the target variable. If both pictures belong to same person, what will happen to equidistant distance? Is that number going to be close to 0 or far from 0?
It's close
Positive
to zero.
sample. Huh? Positive
It's
sample
close to
close to 0. Right?
yes.
And negative sample far from 0. Right? So there is a pattern. Right? There is a pattern, and there will be 1 for the positive sample in the target variable. There will be 0 for the, so the weights in this network will be learned in such a way that when the merge layer, right, the merge layer is giving a number close to 0, the output will try to predict 1. Okay, merge layer is far from 0, the output layer try to predict 0. Like that, the weights will be trained. Right? That is how it understands. So when it understands, right, you can actually take these as the representation, these 128 pixels as the representation, because when positive sample passed, the weights are coming in that way, right? When negative, so it is in sync with the target variable. It's a supervised dimensionality reduction. Do you agree? It's a supervised dimensionality reduction. Do you agree? This is a supervised dimensionality reduction.
Yes, yes.
Right? So that's the advantage of deep learning. Machine learning cannot solve all the problems. Right? If you know the gist of deep learning, right, we can do many things. We can do, these are all experimental. No, will they work, really work? There are some things which are experimental. Why am I trying to tell this is, many people don't know the capabilities of AI and drawbacks of AI, and they're going to the client and trying to say that everything we can do. If you promise something and unable to deliver, it's going to cause a lot of damage. Right? So we need to be careful. We need to experiment with different things and know which works, which will not work, and which is experimental, and then explain the same way to the client. So these are all things will work. These are all things are experimental. In this project, we need to do at least 2-3 experimental things, and then we'll be able to come to conclusion and give you maybe 80%, 90% accuracy. That's how you need to present to the client. Got it? That was not done. That is not being done in the industry now in many places. Many companies are not doing that. Okay. One classical example is most recently my engagement. They don't even know the capabilities of what is AI, what it can do, what it cannot do, and they promised, and they don't even know what they are doing. Okay. So like that it is. Got it right? Got it right? So why am I saying experimental? Because you have this idea, you can apply this idea into many other places. Right? Many other places you can apply this. So this is supervised dimensional reduction. Now, when you train this network, ultimately what is the outcome you are looking for? These 128 pixels, dense one's outcome. When you pass dense, dense one will give you what? It will give you 128 pixels, that outcome you want. Okay. So here I am taking 256 pixels, I think. So I trained the model, I trained the network, and then I fitted the model. See this here? I passed the positive sample, negative sample, and the label. Positive sample is going into dense one. Okay. Negative sample is going to, anchor tag, anchor image is going to dense one. Positive or negative image is going to dense two. Label is common, right? You trained the model. So how is it going? It is going like this. The positive is anchor is going in this direction. Positive or negative is going in this direction. Here we are calculating Euclidean distance, and then we are passing it to the sigmoid function. Why Euclidean distance? I'll show you in a moment. Okay. So Euclidean distance and passing it to the sigmoid function. That's how the network is working. So we implemented Siamese network. We almost implemented Siamese network. It is just that you need to pass pictures and try to do it, and maybe triplet class you need to implement. We'll see that in a moment. Right? I trained this, and we can take the last layer's outcome. I don't know why I did not took it. Let me do that. Where am I? What did I execute previously? So let it run, right? Once after it runs, right, I'll come back and try to show you the pixels or the, the reduced vector, image vector. Okay. So while it is running, right, let us look at the theory now. Okay. So I said I am going to reduce each picture into 128 dimensional vector. You can choose the dimensionality, it doesn't matter. 128 dimensional vector, and then save them into database. When a person comes in front of the camera, I'll take that picture and convert it into 128 pixels, pass it to the network and convert it to 128 pixels, and then check whether this vector is present in the database or not. Okay, so that's the face recognition model. So Siamese network will generate a function that outputs 128 valued vector encoding or embedding, Okay, the distance is the norm of these two vectors, right? X1 and X2. That function, the distance function, is like this. Norm of, right? Norm is nothing but the Euclidean distance of the two, right? F of X1 and F of X2. What is F of X1? This network is F of X. This network is F of, this network is F function. Can I say this network a function? You pass a picture to this network, you are getting 128 numbers. You pass some value to a function, it is outputting something else, right? This network can be called as a function. Do you agree? Each neural network can be called as a function. Do you agree? Each neural network can be called as a function. Do you agree?
Yes, sir.
Right? It
Yes,
has
sir.
got mathematics inside it. You are passing numbers and it's outputting something. So distance between x1 and x2 anchor are positive or negative image. Anchor and positive, anchor and negative. X1 can be anchor, right? X2 can be positive or negative. Can be calculated using Euclidean norm of function 1 minus function 2. Function 1 is the network. Function of x1 and function of x2. Function is the network, neural network we are designing. Okay. So the distance is the norm of the two vectors. Okay. The distance is less, it is the same person, otherwise not. N images in the database need to make n number of distance calculations. Okay. So n number of distance calculations. So a new image came in, you pass it to this network. The new image and all, okay, I'll talk about that. N distance calculations you need to measure. So you new image came in, you pass it to the function, the network, and get the 128 pixels and then compare the distances between that 128 and the 1128 is present in the database. Okay, so that is the network. Now we look at the, let us look at this one. So y cap is equal to sigmoid of wi into f of xik, f of xjk. What is k? Xik, xjk, right? So okay, so okay, got it. So that's where I wrote the network like that. This is actually the Euclidean distance, right? I am passing Euclidean distance to sigmoid function. Then what happens? The sigmoid function will have 1 by 1 plus e power minus z, right? 1 by 1 plus e power minus wx plus b, right? What is x here? The Euclidean distance is the x. Wx plus b. The weight is going to be trained. So that is the function. The y cap function is that one. Okay. Did you understood this y cap? Did you understand this y cap? I think this image I need to change a little bit. Here I need to add the Euclidean distance function and then pass that to the sigmoid function. Did you get this function, guys?
So what is f of x of I,
F
I
of
and j, I and j. So
I
there's
and J are
two
images.
networks.
Xi, Xi is the anchor image. Xj is the positive or negative image.
Okay.
Right? F is the neural network. After passing this image Xi through neural network, and after passing the image Xj through neural network, I am taking the Euclidean distance between these two, and then passing that into sigmoid function. Sigmoid function's y cap is 1 by 1 plus e power minus g, right? So that z is the thing, this is the z thing, right? Wi I should keep here somewhere, right? So this is the x, wx plus b, this is the x, right? Sigmoid of wx plus b, 1 by 1 plus wx plus b is going to be the y cap. Got it? Confusing?
So here the weight will be only one weight.
Yeah, because the last layer in the, after this, right, there is a layer which is actually giving you an Euclidean distance between these two, and that
Yeah.
distance you are passing. So let me try to edit this image and then you will understand. I think I should edit this. No, give me 1 second. I did this notes and then I'm not getting time. So whole day I'll be juggling many things. While doing class, right, I get some idea, but I'm not able to do. Give me 1 second. Let me draw that and you will understand better. So
Sir, here our network is very simple. Maybe because the dimension of the input image is
image complex. So the network is simple. So here, right, actually what is happening here, we have a function that actually is doing Euclidean distance. Actually, I should have written like this. These two are going into this, and this is the Euclidean distance, ED, and one output is coming, right? This is X, right? And then what happens? The sigmoid function is 1 by 1 plus e power minus wx plus b, right? Right? What is this X? That is that X. This box is that one. Got it?
yes.
And that is the Siamese network. Okay. So in this, right, we will have the cost function I have taken was normal, whatever that, right. But in real time, there will be triplet loss function. So let us look at what that triplet loss function in a moment. So take row A, row B. We have seen this, right, and then encode images with the Siamese network, right? F of x, right? This encoding, right? And then pass in sigmoid function. This is the network we train, right? Now let us look at that cost function also a little bit. So optimization function or the cost function. So given anchor image A, positive image P, and negative image N, triplet loss function will make sure that the model is generating weights to identify positive and negative images, right? So triplet loss will make sure this is not. Optimization function generally looks at the weights only. It tries to make the weights as appropriate as possible. Okay. So this distance between A comma P is always going to be less than A comma N, right? What is A? Anchor tag, anchor image. P is the positive image. A is the anchor image and P is the negative image. Distance between 5, the pixels is always going to be less than distance between 5 and 2. Do you agree? Do you agree?
Yes, sir.
So we have alpha here. We'll see. Why alpha? We'll see in a moment. Okay. So what is this distance between A and P? Is a Euclidean distance between f of A and f of P. What is f? The neural network, right? F of A, f of P, right? So you pass negative image, anchor image, positive image, and anchor image through network. But while training is happening, after this, you will not pass y cap and compare, 0 and 1, right? In this data set, right, you have 1 and 0, but you actually, no, in my network, what I did, I passed 1 and 0 here. Okay, I passed the target variable here. See this 1 and 0 I passed and tried to train the network. But if you use Siamese, the real Siamese network, and use the triplet loss function, you will be passing these 128 pixels and these 128 pixels into the optimization function. Okay, got it? The difference between my implementation and real Siamese network. Did you get it? Did you get it? My implementation, I am passing the original 5, sorry, anchor 5, positive 5, label 1, anchor 5, negative 2, label 1, right? And the cost function is binary cross entropy, right? It is just simple, binary class classification it is doing, right? Still the network will learn. These 128 pixels will be learned. They may not be that appropriate, but they will be learned, okay? But if you see here, if you want to use triplet class function, right, the cost function should be defined. Our own cost function should be defined and given there. Okay? This cost function, loss function, or the metric, maybe metric, sorry, not the cost function. Metric should be given. Yeah, sorry. So metric should be given a triplet class. So I actually took accuracy, right? Instead of taking accuracy, I need to build a function, right? Build a function that actually checks this. We can do that, maybe in couple of days, right? I'll implement and show so that we can use this to do phase detection. Okay. So I'm taking Euclidean distance, and then there is an alpha, and then this actually a small number. So hyperparameter is. Okay, we'll look at that. So in some cases, what happens is, if you have two twins working in your company, right? Maybe a couple of teams working in your company, right? The anchor image and the positive image, and anchor image and negative image taken from the two, two of those what you call it as twins. What happens? This distance and this distance. What happens? Anchor and positive image and anchor and negative image, right? We have taken twins, and from that we formed anchor and positive and anchor and negative. Will this still hold true? Forget about alpha. Will this still hold true?
Yeah, it will be, but the difference will be very less.
Very less. Sometimes it may not also, right?
May not also.
Sometimes it may not also. That's where, to make the model more stringent, we actually have to take some samples which are hand picked, which will be kind of close looking, right? We have to take hand picked and then train the model, right? So that the model learns very well. So suppose that we have chosen positive negative samples close to anchor image, right? Twins. Then the difference between these two, Euclidean distance is going to be 0.5. Euclidean distance is going to be 0.51. Only 0.1, 0.01 difference. Okay. If alpha is equal to 0, the network will learn. But if alpha you put 0.2, right, it will actually strive a little more, because if you are adding 0.2 to the 0.5, that's going to be 0.52. Okay. You know that it is positive sample, this is negative sample, because in the data set we already flagged it, and the difference is high because you added 0.2. The model will train a little more, and try to understand better. Got it? This alpha helps you make the embeddings or the encodings more stringent and strong. Got it? Sesiram gar, your question. Got it?
So where I asked if the number of inputs are more.
No, you asked about these 128 pixels may come close, right?
Yeah.
For negative images also, anchor and
Yes.
negative. That will not happen because of this metric, right? You can actually take cast function also, no loss function, cast function, or metric also you can give. If you give metric as this one, right? The model will try to strive to make the metric also, right? So metric it will look at? No, I think. Right? Only loss function. So cast function you need to build like that and then give that custom cast function. And metric also you can use the same thing. Right? Mean squared error is a metric and you can use mean squared error as a loss function also. Like that, you can take triplet class as a loss function as well as metric also. We have to implement that. That changes that additional thing I need to do here. Okay. So the network is trained. So I need to take oh, that's not possible. I'll do that. I need to pass one picture and then I need to pass one pair and take one picture's 128 pixel whatever. Okay, this has been tomorrow. I'll start with that and then we'll move into word embeddings. And this is another exercise. We have to do face detection model. I have done 80% of it. 20% most critical, 20% is pending. Okay. So let me stop recording.